Okay, so hello again. Now I officially start my lecture. And I'm mostly going through slides, but I also write from time to time. Okay, now I should be able to change. Like this. Okay. So for starters, if I want to talk about graph sister algebras, I must remind you what graphs are. These are directed graphs. This is very important. Our graphs are directed. Some people also call them oriented. Some people call them quivers. They are very fundamental structures in mathematics, in combinatorics. They are really omnipresent. They're like vector space, a graph, vector space. These are things that everybody knows, but they go under many names. And of course, depending on your context, I'm not going to write down each time directed graph if all I'm doing are directed graphs. Of course, people who do undirected graphs, we also say graphs and don't repeat undirected graphs, okay? So for us, graphs are directed. So what is a directed graph? Well, it's a quadruple consisting of the set of vertices, E0, the set of edges, which are also called arrows, E1, and the source and target maps. And target map sometimes is called a range map, okay? But I prefer target. So I have a map from E1 to E0. So each edge has its beginning and has its end, all right? This is what orients it. Of course, as you can imagine, a graph is called finite if both sets E0 and E1 are finite. Okay, if any of them is infinite, then you say that a graph is infinite. Okay. Now, at this moment, it doesn't look very motivated, but we will desperately need it when doing graph sister algebras. We need to have three definitions about vertices. So first, a vertex is called a sink if it emits no edges. So maybe I should be able to draw a picture. So I have a vertex. Oops, this is an eraser. I have a vertex and it emits an edge. Well, but it doesn't receive an edge, so it's a sink. If I have a vertex which doesn't emit, doesn't receive, is also a sink. Okay. Sorry, wrong. So this vertex is a sink because it receives but doesn't emit. So this is a sink. This is a sink. This is not a sink. Okay. Now, well, that's kind of clear, and I can just write it down formally. A vertex is a sink if the preimage of the source map is the empty set, so it does not emit an edge. Okay. Of course, you can say symmetrically what a source is, but it's not as important because the definition of a graph sister algebra is not symmetric. Now, an infinite emitter, well, this is a vertex which, of course, emits infinitely many edges. And this is extremely important. We call a vertex regular whenever it emits at least one and at most finitely many edges, okay? Because there are completely different rules of engagement in the definition of a graph sister algebra for such vertices. So it's extremely important to monitor the behavior of regular vertices, okay? And whenever you have irregular vertices, your life is getting much more complicated, also more fun, but more complicated. Okay, I suppose no questions here. Now, so elementary remarks. Sure.
What's the relation between the map S and the line?
This is what I drew was an edge. It wasn't a map. And so, for instance, when I have such a picture, oops, now I still have to choose a pen. Say that this is my graph. It has one edge. So the set, the E1 set is one element set, and it has two vertices. So the source of this edge is this vertex, and the target of this edge is this vertex. That's it. Okay. But I will draw some examples in a second. So now that the maps S and T need not be injective nor surjective, we should never assume such a thing. Then, well, if you like the zero sister algebras, then if both E0 and E1 are empty, we call E the empty graph. And then when you take the graph sister algebra of the empty graph, it's of course the zero sister algebra by definition. But please observe one thing, that the set E1 might always be empty. You might have a graph which has only vertices. But the non-empty graph cannot have the empty set of vertices because every edge must have its beginning and its end. So in every non-empty graph, there must be at least one vertex. Okay. Now, this is a strange thing because I've never seen anybody using uncountably many edges or vertices, but it's not forbidden. So 99% of elementary theory, which I was doing, it doesn't forbid you to have, 2 to the power of continuum edges. Why not? There are non-separable Hilbert spaces. They exist. So you can do such things, but and only at some very, very few places, maybe concerning K-theory, some really advanced theorems to say, aha, the graph might be infinite, but at most countable. Okay. Just like you speak about discrete groups, you would often, say, in the context of Baum conjecture, Paul always likes to say, okay, let my discrete group be second countable. The basis is topological basis is countable, stuff like this. So that's just a warning. Of course, they easily might be infinite. They are very often infinite in real life. Okay, so by no means this is about combinatorics of finite graphs. Forget it. No, that's not what it is all about. We'll immediately have examples of infinite graphs, both concerning vertices and edges. But I've never seen any examples, to be honest, which would say, okay, let it be 2 to the power of continuum edges. No, I don't. Okay, now, and that's something a little bit tricky because whenever you have sets, you can intersect them and take their union. Not the same with graphs. And you can very easily imagine why. Because when you take the intersection of graphs, obviously you intersect the sets of vertices and the sets of edges. And now we have source and target maps, and they have to agree on the intersection. If they don't agree, the intersection graph does not exist. But obviously, if the intersection graph exists, then the union graph exists.
Then what?
The union graph exists. Yeah. So if they can intersect the graphs, then of course you can take the union of the graphs. Definitions are obvious how to do them. I'll spare you. But okay.
So the unions are not disjoint.
No. And we can do push outs, and we have a right category of graphs. Everything works. Okay. So now some examples. So I told you that the source and target maps need not be injective or bijective. So for instance, you can have. Now again, I have to switch on my pen. No, maybe I'll put people to the left-hand side. I hope you're okay with blue. I don't want to waste time finding something else. All right. So for instance, I can have, say, 3 vertices and 2 edges. Okay. So I have V1, V2, V3, and E1, E2. So I have that the source of E1 is V1, the source of E2 is V2, the target of E1 is V3, and is also the target of E2. Okay. So for instance, obviously the source map is not surjective because there's no V3 in this image. Also, the target map is not surjective, only V3.
Why
V3 is not in the image of a source map.
Yeah.
And U and V2 are not in the image of a target map. And of course, the injectivity fails because you have 2 edges with the same ending. And I could, of course, easily do such a thing, but I have 2 edges with the same beginning. So of course, it need not be injected. Okay. What else? Nobody tells you that the source and the target map must be different. You might have a loop. This is actually what very often happens. Okay. Then the source, this is my edge E, and the source of E is equal to the target of E. Nothing wrong with this, quite the contrary. This is what gives you some fun. But you can also have a composite loop, like you go up and up and up. So you have a loop, but we go around. So you have, you can do many things. And you can have, for instance, paths that escape to infinity. Or you can say, I have only 2 vertices, but I have countable infinitely many edges between them. So whatever you want, okay? I'm not sure I can think about any other. There will be plenty of real life examples of graphs, but sort of to illustrate the basics, I think that's enough. Okay. Now, that's what we will need for Leavitt path algebras and for graph sister algebras. There's a concept of the opposite graph, and it's crystal clear. You just reverse the order of your arrow. You say that the beginning is the end and the end is the beginning. But you do it in order to define so-called extended graph. So to define the extended graph, what you do, you say that in the extended graph, you have exactly the same set of vertices as in the graph, but you double your edges. So every edge has its ghost going in the opposite direction, particle and antiparticle, okay? But we don't annihilate. I mean, sometimes we do, but not always. So you have here the disjoint union, and simply you label E1 star is basically the same set as E1, but you just label it with star, okay? So you double your set of edges, and now you say, aha, that for these starred edges, the beginning of a starred edge is exactly the end of the edge, and the end of the starred edge is the beginning of this edge. All right, so here the formulas are written down. So for a lawyer to verify that everything works, yeah, you can check everything holds. And now you can think about it, you know, as actually the union of a graph and its opposite. When you intersect the graph and the opposite graph, okay, then the intersection of edges will be empty, right? Because in the opposite graph we have the star edges. And in the graph, you have non-starred edges, so intersection is empty. But the intersection of vertices is the whole set of vertices. And of course, when you have the empty source of the empty domain of your maps, that's just the empty map, okay? So you have intersection graph, it exists. I'm giving an example where you can intersect the graph E and its opposite.
It does the graph with vertices, no edges.
Exactly, yeah. As I told you, it can happen, yeah. So the intersection exists, so therefore also the union exists. And you can look at this extended graph as the union of a graph and the opposite, okay? And this is very important because in order to get graph sister algebras, you have to take path algebras, but of the extended graph. You need adjoints in your sister algebra, okay? Okay, haha. Now some examples. Look, if my edge is simply, if my graph consists of one edge and two vertices, as drawn in the picture, then the extended graph will have the same set of vertices, of course, and you'll have this ghost edge going the opposite way. Yeah?
But can you scroll up?
Up.
So you said that the union of E and E
Up.
is E.
Is E bar. I mean, here you see.
Okay.
I'm sorry about this. Yeah. Still, this is very nice technology because I don't have to alternate between the whiteboard and slides. You see? Okay, let's continue. If our graph consists of one loop, so one edge and one vertex, well, then we have a ghost loop. And here I don't have to reverse the direction because these graphs are not planar graphs. They are oriented only in the sense that I know what is the beginning and what the end is. You should not imagine that I draw these lines in space on a plane and that you have some braiding between the, no. Crossings happen only at the vertices. Whichever way you weave your edges is irrelevant. Okay? It doesn't happen in space. Well, and so that you don't think that if you already have an edge going one way and then another edge going the other way, you should not think that that's it. But if you do the extended graph, then you still double the amount of edges. So now you have 4 edges. Okay, so you have 2 going right to left and 2 going left to right. Okay. Okay, so these are graphs, and now in order to do path algebras, you have to do finite paths. Of course, you can also do infinite paths. You can do infinite paths left and right, but let's not do it. It's not needed for my purpose. We take a graph, any graph, And we say that the finite path in E is a finite tuple, or if you wish, a finite sequence of edges satisfying the following crucial condition, that the end of one edge is the beginning of the next edge. Okay? So T of E1 must be the end of E2. The end of E2 must be the beginning of E3, and so on and so forth. Okay? So this is what you call a path, a sequence of edges with this property, that the adjacent edges share a common vertex. Okay? And now if you can very easily extend the source and the target maps from edges to all finite paths, simply by saying that the beginning of a path Pn is the beginning of its first edge, and the end of the path Pn is the end of its last edge. Okay, so this is what is written here. And the length of a path is the size of this tuple. So this is a path of length n. And it's very important that vertices are considered as finite paths of length 0. It's very important for a terminology that you consider vertices as paths. Okay, otherwise you'll be very inconsistent. Okay, so now how about loops? A path P is called a loop if P is not a vertex. So vertices are not considered loops, never, because oh wow, this is a path which begins and ends at the same place. No, we don't call vertices loops. Okay, a path P is called a loop or a cycle. That's very confusing. People do not agree. For instance, I believe, like Wojtek Szymański, that loops can be paths that share the beginning and end of any positive length. But other people believe that such things should be called cycles and loops are only at length 1. This is crazy. It's like with natural numbers. You can never know whether 0 is a natural number. Forget it. It's a religion. It's somebody's belief. Okay. I believe that loops can have any length. Wojtek Szymański is one of the best gurus in sister algebra. Sister algebra does the same. But you can have examples of 10 other scientists who believe no, loop has length 1.
So loop for you has length 1.
No, for me, loop can have any positive length. But other people will call the cycle. For me, it's confusing. I mean, cycle sounds like cyclic homology. What are you talking about? Anyway, or cycle of lectures, right? A loop is a very nice word. Okay, and so any path that has this property that its end and its beginning coincide, and it's not a vertex, okay? Because obviously you can say that the beginning of a path which is just a vertex is this vertex, and the end of a path which is just this vertex is this vertex. It's kind of trivial, yeah? So you could call a vertex a path, but we do not, I emphasize. And now,
I think that the vertices are paths for you, but not loops.
exactly.
So it is a path.
It is a path, but not a loop. Yeah, exactly. But that's a bit confusing. That's why I sort of stress it.
The source of the path is the source of the first.
Exactly.
Okay.
But you can say, okay, so what is the source of the path which consists of one vertex? Well, it's just this vertex. What is the end of a path which consists of one vertex? It's just this vertex. Maybe I should have written it somewhere. Okay, so yeah, I can do it. So source of a vertex is a vertex and is also the end of the vertex. Yeah. It's one of these notational issues, like the sum over empty set is 0, the product over empty set is 1. I mean, you need this notation, otherwise your calculations are crazy, inconvenient. I should be able to have just width. Let me see if I can add. Thickness, let's make it 1 point. No, 13. How about 0.5? And how about some different color? I don't know. Black. Okay. Oh yeah, it's much better. I love playing with toys. Sorry, Luke. I know you don't, but I love. Okay. Now, it's again, it's not motivated here. You might think that what a weird definition it is, but it is very important in some graph system algebraic theorem that hopefully I might touch upon on Thursday. Okay, so it's very important to understand what it means that loop has an exit. So a loop, which is a non-zero length path, which is the same beginning at the end. We say that it has an exit whenever there exists an index j. So there is one edge in this loop such that there is another edge with the property that the beginning of this edge in the loop coincides with this edge f, but this edge f is different from the edge in loop. Okay.
Maybe some drawing.
I'll have
Okay.
empty slide later on, so bear with me, please. Yeah. And of course, yeah, I agree that calling that the graph without loops is called a cyclic. That's a nice name. Loopless would be a bit awkward. You could say loopless, but nobody does it. It's called a cyclic. If your graph has no loops, it's called a cyclic. Yeah.
Acyclic.
Acyclic. Yeah. Not acyclic. Acyclic. Okay. Okay. And now, once you know what the path is, it's very important to take the space of all finite paths, vertices included, mind you, and note that the space might be infinite even if E is a finite graph, when both E0 and E1 are finite. Okay, whenever you have a loop, you can go around as many times as you want. In fact, we have a proposition that if E is a finite graph, then the space of all finite paths is finite if and only if there are no loops in it. So one way implication is obvious. If you have a loop, of course, your space of paths is infinite because you can go around your loop as many times as you want. So you can have paths of any length you want. So you have infinitely many paths. So one way implication is obvious. But now how about the other way around? Assume that there are no loops, okay? What happens then? If there are no loops, then I claim that then the edges in any finite path cannot repeat themselves, okay? And if they cannot repeat themselves, you are done. Your combinatorics tells you that you have finitely many paths, right? Because you have finitely many edges, your graph is finite. If in any of your paths, your edges cannot repeat themselves, that's it. You must have finitely many edges, many paths, finitely many finite paths. Okay. So see why if there are no loops, the edges cannot repeat themselves. Well, assume the contrary. Suppose the contrary. Suppose that you have EI equal to EJ, but index I is strictly less than index J. Okay. But then what happens is because EI is equal to EJ, then obviously the source of EI is the same as the source of EJ. But remember the path condition. Okay. You must have that the target of the preceding edge is the beginning of the edge. So target of EJ minus 1 is the beginning of EJ. Okay. But now the path which goes from EI to EJ minus 1, and mind you, J is strictly bigger. So in the worst case scenario, you have at least one edge, EI. Yeah, it might be that J minus 1 is equal to I, but no less. Okay. And then you see that the beginning of EI is equal to the end of EJ minus 1. That's it, it's a loop. Okay. So this ends the proof. I'll skip the trigger parts. Okay. That's the only real argument. Okay. However, it's a bit more subtle when you fix the length of your path. Okay. So first, let me draw your attention to the fact that when you take the set of all finite paths of your graph, it decomposes into this disjoint union, which is labeled of subsets labeled by length of a path. So any finite path has its length. So first you have paths of length 0, and you have paths of length 1, length 2, and so on and so forth. And you scale like this to infinity. And of course, it might happen that for some sufficient large k, you have empty sets, right? Still the formula is correct. Okay? The space for any graph, the space of all finite paths decomposes into such a disjoint union. And here you can have some fun with combinatorics of counting paths of a given length, all right? So if you like combinatorics, let me make an advertisement. Yeah, on YouTube you do many commercials. So since we don't on YouTube, I'm making a commercial right now. I advertise a product, and the product is my tomorrow's talk about the combinatorics of graphs. So 5 p.m. this room with Ludwig as the chair. There will be.
That's on Zoom.
It's on Zoom also. You can also join on Zoom. I'll talk about counting paths in graphs with loops. Okay, and pure combinatorics. So no knowledge necessary whatsoever. And what is amazing about combinatorics, it's a bit like, playing chess. I mean, you don't need to understand anything abstract, but still it's intellectually very challenging. So that's how it goes, combinatorics. So I strongly encourage you to join us tomorrow. But going back to my lecture, if you look at the set of all paths of length k in a given graph, this is always finite whenever the set E1 is finite. Whoops, the set E1 of edges. Okay, sorry about this. The set of edges, of course. You can have as many vertices as you want. It's irrelevant. Okay. And here, in fact, you have a more precise claim, proposition is a trivial one. If E is a graph with n edges, okay, so n is a finite number, and I choose k, of course, I cannot have a path which is longer than the amount of all edges unless I have a loop. So let me take a k which is at least 1 and at most n. Then you can easily check that there are at most n to the power k different paths of length k, and the bound is optimal. Okay.
So graph is no loops. There's assumption.
No. 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 I just say that the graph has n edges. That's the point. That's the point. Once I fix the length, I'm finite, even though I have loops. Okay. So this is an example of trivial combinatorics. When you don't say anything about the length of your loops, then the combinatorics is trivial. Tomorrow, I'm going to prove a theorem under the assumption that when I'm counting paths of length k, I do not admit loops shorter than k. Then combinatorics is really fun. Okay. So, well, obviously, when you take any path in E of length k, and you have n edges, then you simply write a k letter words using n letters, right? N is your alphabet, and k is the length of your word. So obviously you have n choices for your first letter, n choices for a second letter, and so on and so forth. So you cannot possibly have more than n to the power k many paths. But, and the bound is optimal because you have this Hawaiian earring. Okay, that's the Hawaiian earring graph. And you have simply n loops with just one vertex at the beginning and the end of all of them. And this is how you can write any path of length k. Take E1 up to n, then for the next word, E1 to n, you obviously have n to the power k choices. So the bound is optimal. Okay. And mind you, I have loops, and if I would look at all paths, all finite paths, is obviously infinite. Because I can twist around for as long as I want. If I just don't fix my length, then I have obviously infinitely many finite paths. Okay, so now these examples. So this is my empty slide so that I can do the examples. So well, this is a path, the lazy path, just one point. You can have the usual path, so you go like this, like this, like this. That's also a path. This is not a path. So V and W are kind of connected, but this is not the path, right? Because here the ends agree. So the end of E is equal to the beginning of F. Sorry. Sorry, is equal to the end of F. So that's no good, right? It must be that the end of one edge is the beginning of an next edge. So this doesn't work. Well, you can have the following situation. This is a very important graph. This is a graph of a Teplitz algebra. I have E and I have F. So I can go around the loop as many times as I want, say n times, and then exit by F. This is a nice path. Twist around n times and then exit. Okay. So this is the quantum disk sister algebra, if you take the graph system graph. Now, if I draw one more loop here, this is the graph of quantum SU2 group. Okay. And then you can say this is a, I don't know, EFG. And then you can write GM. And this is also a path. It's a path from V to W. Okay. And you see that you have obviously infinitely many paths interesting paths, even though you have just what, 3 edges and 2 vertices. Okay, and this is a very important quantum space. This is the famous SUQ2 sister algebra. What else I should have told you about paths? Some examples. Yeah. Well, but I can actually draw it here. We are talking about this. Yes, loops with an exit. So okay, I remember now. So I can have a loop. So a path of length bigger than 0, the same beginning and the end. So this loop has no exit. But now if I draw such a thing, so this is my E1, E2, okay, this is my path. But if I draw an F, which is not part of this loop, I mean, F has the same beginning as E1, but it is not E1, all right? In fact, it doesn't have to go away. I mean, I can have it, this F joins here. That's also fine. You also consider it an exit. I never told you that the end of F must be different than the end of E1.
But it can be a loop from E1 to E1 also.
Yeah, but it's not part of the loop, you see. My loop, I have another loop lurking here. I can substitute F for E1, but then it's a different loop. For the loop which consists from, you know, E1 ... to En, for this loop has an exit. Okay, this is exactly what you have in the definition. See, we say that the loop Pi with indexing set I has an exit if there exists an index J and a vertex F such that this edge, which is part of a loop with this index J, so EJ, that its beginning is the same as the beginning of this edge F, which is, you know, not part of I mean, it just says, yeah, I mean, just says that this is not, to be honest, now I'm puzzled because I'm wondering whether F is forbidden to be an element of a set of edges constituting a loop. That's not clear. Probably it is forbidden. I must look it up. Okay, so I will look it up because it's needed for a specific theorem about which is very important about the injectivity of certain star homomorphisms. Okay, so we are not doing it just for the sake of graph theory. We're doing it for graph sister algebras. Okay, according to this definition, I could, you know, go around with edges in my loop, and then I can have alternative edges, and it should still be an exit, but I'm not sure. Yes.
So when you say a graph is a cyclic,
Yes.
it doesn't lose in the sense of like one path from one vertex to itself, or in that.
No. Loop is I clearly defined the loop right here. The loop is a length, positive length path which has the same end at the beginning. Period. That's it.
You also could loop like.
Yeah, that's also it has all the same end at the beginning. A path of length 1 is a path.
So loop are paths which end is beginning.
I don't understand your problem. I mean, you can.
Like one, not that, I mean, not from the vertex to itself.
I mean, this is a loop. One edge, one vertex. This is a loop.
Okay.
And the length is 1.
Okay.
But this is also a loop of length 2.
Okay. So.
And if I go around million times, I have a loop of length million.
Yeah. Okay. Nice. But then basically it has to be something like a portion of a line to be a cyclic, something like this.
What is the portion of a line? What line?
What is a cyclic?
Lack of loops.
So basically a line,
Why a line?
something straight.
Well, it can have a tree. Why a line? I mean,
Okay.
that's
Mhm.
what's wrong with this.
Okay.
What's wrong with just dots? Okay.
Yes.
Yeah.
Okay. Yeah.
But it is true that the moment you ban loops, okay, your theory becomes a little bit boring. I mean, you no longer really say graphs, you say trees. Yeah, and you really change the name of the game. Once you ban loops, your life becomes much simpler. Because basically that's all you can have. You can have trees and you can have disconnected trees and vertices floating around. That's it.
I'll find on graphs.
No. Okay. All right. So we have a certain mystery here, because according to this definition of a loop with an exit, I could do the following: say that this is my E1, E2, and now I have E3. So E3 somehow doubles my E1. So according to, and I say that my loop is E1, E2, E3, sorry, E1, E2, E3, E2. This is a nice loop, okay? I go E1, E2, E3, E2. That's a loop of length 4, right? What?
So you want me to show the drawing if I don't understand.
Okay, maybe I'll make it more clear. Whenever you touch a connected component, it vanishes. Okay, I hope that's enough. But it's fun, isn't it? Okay, so say I go E1, I go E2, I go E3. But here I also put, say, E4. Okay, so I can just take the boring path E1, E2, E3, but I can do this. I can go E1, E2, E3, E4, E2, and E3. It's a loop. Okay. But now, according to the definition I gave, I have an index, j equal to 1, okay? And there is an edge which has the same beginning as E1, and it's not E1, namely E4. But it's also part of my loop. So to be honest, now I'm confused. According to this definition, this is a loop with an exit. But I will double check if I miss something wrong. I'll check if I missed it, because that's very easy to fix, right?
Target of this exit loop.
Forget the target. It's enough to say that SEJ is equal to SF, and instead of writing that DJ is not equal to F, it suffices to write that F does not belong to the set of edges constituting the loop.
No, I'm not. I disagree, because you still can consider the loop, the tree before, the tree below, and then with this definition, still F is an exit. Instead, maybe we can have to say that target of F is different from any element of the loop, from any point.
Yeah, but I'm pretty certain. Yeah, I know what you are driving at, but that's definitely too much. This is an overkill, or what you suggest. Because you don't. That's of course a good example of an exit. Yeah, that's kind of really, you think like a highway, driving a car, and you really make an exit. Okay. But no, I mean, I'm certain that it's completely fine if you have a detour.
Okay.
That should be fine, as long as this guy is not part of your loop. Say that this is paid for part of a highway. It is not part of your loop. Then it's definitely with an exit. What I'm not sure about is this example, when this sort of F is also an edge, is part of my loop, which I can easily draw like this. That puzzles me right now, to be honest. Okay, but we'll get back to it. We'll see if there is someone on chat. Will you upload the recording? Yes, I will. Yes. Okay. Now, path algebras. So now we leave the combinatorics of graphs and we enter the territory of path algebras. And I know, I promise you that I'll be working only with the field of complex numbers, but here it looked like some criminal action to consider only complex numbers because we're not doing any analysis yet. Until I get to star algebras and do completions, forget it, can be any field. Really, I mean, this is one of the advantages of doing path algebras and Levi path algebras, that you can play around with many fields, okay? So let K be a field and E be any non-empty graph. I don't want to enter into the discussion of zero algebras, okay? And now consider the following vector space. You take all finitely supported maps on the set of all finite paths in your graph E, okay? So if you are finite and acyclic, then finitely supported means nothing because you have a finite domain, right? But it suffices that you have one innocent loop, and you already have to say, aha, my space of all finite paths is infinite, but I take only finitely supported functions, okay? So FP is different from zero only for finitely many paths, all right? And here the addition and the scalar multiplication are pointwise, right? These are functions, and functions you can add and multiply by a scalar. And this gives you a structure of a vector space. Moreover, it is completely obvious that if I take kind of characteristic function of a point, this gives me a linear basis. So a function chi p, an element of ke, where p is a path, has a value on a path q, 1 if p is equal to q, 0 otherwise. Okay, so that's the characteristic function Dirac delta, if you want. You have you have your set, but you distinguish one point p here, and the function is 0 everywhere except that at point p is equal to 1 and 0 everywhere else. Okay. And obviously, the set of all such elements gives you a linear basis. That's a trivial exercise. I deleted it. So, yeah. This gives you a linear basis. Okay, you seem to be puzzled.
Yes, finite paths.
Yes.
Like this disjoint union, then finite.
Sure.
So, like this set of function is not finite.
Well, we need a set of functions.
Like the key P.
Of course, it's whenever your set is infinite, the set of functions on it is also infinite, even if they are finitely supported.
Is the basis in the sense of parallel?
No, it's just the regular basis.
Maybe it's the regular basis.
Yeah. So finite linear combination.
Yeah.
Okay.
Because your function is finitely supported, it suffices to take finitely many p's to have them in the span.
Mm-hmm.
Okay?
Yeah.
Okay, good. Sure. Okay, but that's boring. This
It's
is
just the, we can say, the free vector space.
voila.
Or, yeah.
Exactly.
Okay.
Exactly. But I prefer functions, yes. Typically, people would say, yeah, this is a free vector space generated by the set. But I don't like it because to me, it's a question of what it means, vector space generated by a set. For me, that's a construction. All right, and I have a proposition for you. Well, I claim that with this recipe, I get an associative algebra. So I have a vector space, and in order to turn a vector space into an associative algebra, all I need to do is to define a bilinear pairing, which has this property that it's associative, okay? And because it's bilinear, it suffices that I give my formula only on my basis elements. And that's precisely what I do. I define the bilinear map on basis elements, chi p and chi q, by saying that if the end of p is the beginning of q, I go by concatenation of paths. Now I have a pq path, because the end of p is the beginning of q. And I have a pq path, the concatenation, and chi pq is the result of multiplication. If the end of one path misses the beginning of the other path, poof, they miss each other and multiply to 0. Okay. So maybe it's good to draw. I have one path. Whoops. I have a path P, and I have a path Q. So chi P times chi Q is 0. But if this is my path R, then chi P times chi R is chi PR. Okay. So that's it.
So you put composition
Whenever I
to
can.
right. So first
Yeah.
P is the
Yeah.
first. and
Yeah.
then
It's not like Arabic or Japanese and down.
more like composition of params.
Okay.
So this is the base, it's like a convolution line.
Yeah. Yeah, I mean, it is a theorem that all graph system algebras, or most of them at least, can be viewed as groupoid, convolution groupoid system algebras. Yes. Okay, now some elements.
Question before you move on, Piotr, sorry. It's so we've got a bilinear map here. Would we be able to consider, and this is a bit of a tangent, but a tensor product space where we've taken the quotients so that this becomes a linear map? Would we then have a valid tensor product space as well? Yeah. And has this been investigated at all?
No, I mean, there's nothing to investigate. I mean, saying that instead of bilinear map, you take a tensor product and the linear map doesn't change anything. We already had a long discussion of what you mean by multiplication, a bilinear map or map on the tensor product. I don't want to go back to it. But you raised a question which, I mean, let me reformulate your question into an interesting problem. Namely, later on, when you go into graph system algebras have one, I mean, they have many awful properties, they have many beautiful properties. Nothing is perfect. When you buy a super fast car, it's not a good boat. When you buy a very good boat, it's not a good car. I mean, either it's good for the water or for the highway. It's really hard to have something universal unless you have Star Trek technology. One of the things which are really troublesome with graph system algebras, they are not closed under tensor products. So the tensor product of graph system algebra is not ever, unless you have a point. I mean, unless you tensor complex numbers, unless your graph is one point. So except for trivialities, it's never a graph system algebra. However, this is why people invented colored graphs. So you say that your sets of edges have n colors. And then there is a definition of a so-called K-graph, K-colored graph. And what happens is that there is a definition of a Cartesian product of a K-graph with an L-graph to yield a K plus L graph. And guess what? The tensor product of a higher rank graph system algebra of rank K with a higher rank graph system algebra of rank L is what? Is a higher rank graph system algebra of rank K plus L. Yeah.
Right.
So
thank you so much,
this thing, yeah.
One color is particular case of color graphs. Why does it less than one color?
Well, because the moment you take the tensor product, you should really remember the slots. And to remember the slots, you must use different colors.
So for me, one black color is a different color.
Yeah, but it's a matter of fact. If you take the tensor product of a Teplis algebra, you will not get the graph system algebra. There's a no-go theorem. For instance, the set of classical points cannot contain a torus of higher dimension than 1.
But you said that colors can allow us to take the tensor product.
Yeah, but there's a different theory. I mean,
But one color, one black is a color.
yes,
Why does it work for one color?
because 1 plus 1 is 2. We are adding, not multiplying. You're adding. So if I have a one graph system algebra and one graph system algebra, take the tensor product, I get a 2 graph system algebra.
So with two colors.
With 2 colors. Yeah, because you're not multiplying, you're adding the colors. Okay. So this is sort of what matters in the tensor products. Here, there is absolutely nothing interesting happening. But it is a nice exercise. It's you should really compute it, but it's associative. Right? And mind you, I don't claim that it's unital, and generically, it's not a unital algebra. Okay, I hope I answered your question. I answered my question, but I behave like a politician. You ask me a question which is inconvenient, so I turn it around and ask a question which is convenient. Answer a question which is convenient. Excellent. Okay, so by construction, the dimension of your path algebra is just the number of paths. That's it. Okay. Because we defined a linear basis. We labeled elements of a linear basis of this vector space by paths. So obviously the dimension is the number of elements in a basis. By the way, this is an extremely beautiful theorem which works for fields but not for rings. That indeed in absolute generality for any field and with any power set, okay, if you have a basis of power x, where x is a cardinal number, then any other basis has the same cardinal number as the power. If you go to Bourbaki, this is a really beautiful, I mean, it's trivial in finite dimensions, that's what you did in high school, but go to arbitrary dimension, I mean, 2 continuum, whatever, This is very beautiful. Yeah. When you have a vector space, you really have a dimension. And I'll show you today that when you have a ring and a free module, dimension does not exist. Okay. Next elementary fact.
This most concrete man. I mean, that's what this dimension.
Why?
It could be infinite, right? But it's somehow countable.
But I don't see what's your point.
If the vertices is countable.
Yeah, but it can be uncountable. It also works.
Could be infinite, right?
Yeah.
Okay.
Yeah, can be anything. I told you that, but I don't even assume that I have countably many edges. Yeah. And now, because of this proposition we had earlier, you see that this path algebra is finite dimensional if and only if E is finite and acyclic. Of course, if E is infinite, it cannot be finite dimensional because we'll have infinitely many vertices or infinitely many edges, and already your space of paths will be infinite. Okay, so dimension infinite. But if E is finite, it's not enough because we can have loops. Okay, but we have this proposition which we kind of proved as well. No, here. Fp is finite if and only if there are no loops in E. Okay, next. Aha, when is it unital? And that's a beautiful exercise. And it works exactly the same way for path algebras, for Levitt path algebras, and for graph sister algebras. So please allow me to prove it to you on Thursday for graph sister algebras. So the proofs are identical. Okay. So path algebra is unital, and its unit is the sum of all length 0 paths, or Chi's labels by all length 0 paths, if and only if E0 is finite. Right to left is kind of easy, because if E0 is finite, the sum is finite, and I can just add up all these basis elements. Nobody can stop me. And then I can just multiply. I can see that it works. Okay, and that's actually very easy because. So let me maybe draw it here. I take this sum, and I multiply it by, say, any chi q, right? I mean, anything is a linear span of chi q. So if I can show you that it's 1 on the basis elements, it's 1 everywhere. Okay. So look what happens. Obviously, Q is a path. Aha. So it has its beginning, right? So if I look at the set of all vertices, well, then SQ must be in E0. So there will be one element which will be precisely chi SQ. And chi SQ times chi Q is obviously chi Q, because I have a path which is a vertex, and I have a path which starts there. So a vertex times a path which starts there is this path which starts there by concatenation. Okay. However, for any other vertex, so any other vertex is different from the beginning. So any other vertex times this path is 0, because the end of this path is this vertex, and it's not the same as the beginning. So this is from the right, and from the left, instead of SQ, you take TQ, the same argument. So it's a two-sided unit. It's a bit more tricky and a bit more fun to prove the opposite implication. Namely, to put that if E0 is infinite, then this is a non-unit algebra. You just get a contradiction. You assume that E0 is infinite, you suppose that there is a unit, and then you prove that it's false. That's fine. Let's do it later on. I mean, how to do it for graph system algebras? It's the same argument. And this is important for you to remember, whether you talk path algebras, conpath algebras, Levi path algebras, relative conpath algebras, unitality is always tantamount to finiteness of a set of vertices, and the unit is also always this animal. Yeah, that's your unit in whatever flavor. And that's because when we go into relations, our relations always involve edges. So if I have no edges, relations don't touch. Okay, and there are no edges in this set, only vertices. Okay. This is another exercise, but this one I'm not going to do. You can convince yourself very easily that the path algebra of E is commutative if and only if either you have absolutely no edges, when it's obvious, you just have a function algebra, finitely supported on the set of vertices, and you have usual pointwise multiplication, or each edge is a loop starting and ending at a different vertex. So, I mean, you can have one loop, another loop, and another loop, uncountable many of them if you want, doesn't matter. The point is that these loops will multiply to 0. And themselves, they'll commute with themselves. I mean, everybody commutes with himself, herself, right? So EE is EE, FF is FF, but here EF is 0. So that's it. Obviously, I'm giving you examples of commutative algebras, but to prove that they're all of them, well, we have to do the exercise. But I'm not going to. Okay, so these were elementary facts.
So as soon as there is a loop, so that would be
As soon as you have an edge which is not a loop, it's not commutative. Yeah.
As soon as we have edge.
Which is not a loop. I mean, that's it.
Okay.
If you have,
So that this is joined by
that's it. It's already non-commutative. Yeah.
See this kind of algebra as a sort of extension of like the algebras with the convolution and a set of like if we have, for example, that our graph is also a group, for example, for some reason.
What do you mean, a graph is a group? I don't understand.
Yeah, like the edges, like the vertices are elements of a group.
But how does it influence the multiplication structure? There's
Because
no
in that
bearing
case-
here.
In this case, I can like L1.
No. It's completely you are off board because you see your vertices are just like the importance. That's it. They multiply E squared. V squared is V, and V, they are orthogonal idempotent, and VW is 0 unless V is equal to W. So any group structure you might have on the set of vertices is irrelevant for this multiplication.
What I mean is like a good function on this set, which happens
Which
to-
set? Which set?
The set of vertices,
Okay.
which happens to be a group.
Okay.
Then I have L1 function on this group and the convolution. Okay.
It has nothing to do with this algebra.
But this is like when we don't have edges, like for example, the unity defined is basically the Dirac delta with convolution.
No, that's the sum of all vertices.
Yeah, because like this already encoded in the convolution. Because your definition is just attaching paths,
Yes.
but like this procedure of attaching paths is encoded in the convolution.
How?
Because it's exactly that sum.
I completely don't follow.
Like it also remarked the fact that the structure was similar to a convolution.
Yeah, but it's a complicated theorem after we get ideals and so on and so forth. That's it reminds a little bit of a groupoid because you can think about a graph as a small category, And then you can think about composition of paths as composition of morphisms in a small category. And a group oil is also a small category. So there are some resemblances. But to say that a graph algebra is a convolutionist algebra is a deep theorem, by far non-trivial. You cannot possibly fathom at this stage how it looks like. And just because you can have some L1 space on a group, it's completely irrelevant to this algebraic structure.
I think here is the function on path, right? So the function on vertex is also different. So that's the
Well, but actually, as you said, when there are no edges, your algebra becomes right.
Yes.
Yeah, basically you can talk about paths even if you don't have that.
Even if you don't have edges. Yeah.
So, and kind of claim that this should be a sort of.
So maybe it's
Yeah,
a
well,
relation indicates.
But it's just a commutative function algebra. That's it. Finitely supported functions on a set. That's it. There's no L1 structure. There's no analysis here. There's no convolution. It's just commutative pointwise multiplication. I have a set and I have finitely supported functions on the set. And I multiply these functions component-wise. That's it. That's the algebra, commutative algebra.
If there is additional assigned groups, like it will be by algebras and something.
That T
Phi.
Phi. B.
It's just a basis. This is just
No. But
Yeah.
it's like how can be an element that basically is zero somewhere to be an inverse of something.
but why inverse? This is an algebra. I'm not having inverses. Almost no elements are invertible.
It's the
Unit doesn't mean
That you have a unit doesn't mean that elements.
but in some sense, something like zero.
But look, I mean, just that you have a unit in your ring, it doesn't mean that you have plenty invertible elements. I mean, in any polynomial ring, the only invertible elements are multiples of identity. That's it. Nothing else is invertible. No polynomial is invertible. You have to go to rational functions to be invertible. This is a very non-invertible algebra. Almost nothing is invertible there.
In the case when there's just the vertices, it's like for every vertices you have a copy scale
Yep,
of your
exactly.
theta and some of it.
Exactly. It's k to the power E0.
Yeah. Just this.
It E0 is fine.
And the multiplication is every element with itself is one, maybe, and all the others.
Is that pointwise multiplication? You have functions on a set and you pointwise multiply. F times g of x is f of x times g of x. That's it. And this follows from that recipe. And in fact, I'm just talking about it. So function algebras. So if you have no edges whatsoever, then KE is the commutative algebra of finely supported maps on E0 from E0 to K. Yeah, and you multiply just as I said. I mean, F of F G of X of E, whatever, is equal F of E times G of E. That's
The right hand side is product in K.
Yeah, this is a product of functions, okay,
Elements of K.
of elements of KE. And here's product of elements of the field K. Yeah, that's by evaluation. And that's a triviality to check it with this concatenation recipe. Because the concatenation recipe tells me that when I have no edges, all points multiply to 0. So chi p times chi q is always 0 unless p is equal to q, and chi p times chi p is chi p. Yeah, these are like you say you have a set. You have 3 elements in your set. That's your E0. And when my basis has 3 elements, I have one function which is 1 here and 0 there. I have another function. Sorry. So this will be my one function. This will be my second function, and this will be my third function. And when you see how we multiply, they all are orthogonal projections. They multiply to 0. And when you take the linear span, and you multiply functions, you'll see that it's a pointwise multiplication. No convolution, no L1, nothing. Okay, let me continue to something more interesting. I mean, after all, we are talking non-commutative sister algebras here. Well, we're not started yet, but it's a good beginning that whenever you have a graph which is just a path, say from V1 to Vn, you have n edges and n, sorry, you have here, you have what? You have n minus 1 edges and n vertices, okay? So then the path algebra of such a graph is the algebra of upper triangular matrices. So Mij is non-zero whenever I is bigger than j. And you can verify that you have an algebra isomorphism by sending chi Pij, because what are all paths here in this graph? If I fix your starting point, and if I fix your ending point, I have only one path to connect them. Okay, so all paths are Pij, where I and j are indices. If I is equal to j, then I just have a vertex. If j is less than I, forget it. There's no going back. You can only move left to right. I cannot go from Vn to V1. Okay, but I can go from V2 to Vn, from V2 to Vn minus 1, and in a unique way. Okay, so these are my Pij's giving me my basis. All right, and guess what? I map chi Pij to the elementary matrix Eij. Right, that's the elementary matrix. It has 0 everywhere except for a slot, the row I and the column j, where you have 1. And you can entertain yourself to see that the isomorphism of matrices. First, you see that it's a linear isomorphism because I'm mapping basis to a basis. So it's obviously a linear isomorphism. Okay. And to see that it preserves multiplication, well, I can multiplicate by concatenation. So I write what is f of chi pj, chi plm. Well, by concatenation, chi pj times chi plm is obviously Dirac's delta j and L, and then beginning must agree to concatenate. And then you remove this middle guy, and then you have a path from I to n. Okay, so you have chi pim and Dirac's delta, the Kroneker's delta, delta jm, right? And then you map it to the elementary matrix EIM. But you should also remember how I multiply elementary matrices. Eij times ELM is exactly Dirac-Kroneker's delta JL and elementary matrix IM. That's multiplication of elementary matrices you remember from school. And then obviously just f of chi Pij times f of chi PLM. Okay, and this is for any indices. So if you have this kind of a graph, then your path algebra is the algebra of upper triangular matrices of size n, where n is the number of vertices. Well, you can do lower. This is a question of convention. No, not all. No. That's because you have no path going backwards. And this is why we need an extended graph to have really full sister algebras. Okay, we're not there yet. We don't have an adjunction yet. Okay, and in fact, we are not going into path algebras, but you have some structural theorems that in fact every path algebra is a kind of upper triangular matrix algebra. Except that these guys, the entries are not fields. They are bimodules. But you can make sense out of it. But we are not studying path algebra, so just do the basics, okay? More examples. The polynomial algebra, if your graph is just one loop and one edge, then the path algebra is just the polynomial ring in one variable, right? Chi v is just 1 in your algebra. Obviously, even by this formula that the sum over all vertices gives you 1. Well, here the sum is over one element, so chi v must be unit of this ring, and it is. So it's x to the power 0 if you want. And the only paths you have are powers of e. So this is, maybe I should write it, this is my edge e. Okay, this is my vertex e. No, I wrote it here. Here, v and e are respectively the unique vertex and edge of e, all right? So the only paths you can have is v and powers of e. So, well, chi nth power of e is mapped into nth power of your variable x. That's it. And this way you get, it's again commutative. Remember, I told you that if you have no edges or your edges are loops that begin and end at different vertices, you are good. Of course, I could have some other loops at other vertices, but it wouldn't be a polynomial ring in n variables. It would be something funny. It would be, I would have to divide, you know, xi and xj would always multiply to 0. Right? So that's kind of funny polynomial ring. I didn't like it.
How is the real polynomial ring in a variable? Flower on
What do you mean, a real polynomial?
well, how would I draw the polynomial algebra in two variables?
You cannot. I mean, not every algebra is a path algebra.
Really?
No.
And what is the flower with two?
Here have it. It's a tensor algebra. But that's the answer to the question. I answered the question before you asked it, which means I'm moving faster than the speed of light. Back to the future. Okay. So tensor algebras, non-commutative polynomial algebras. That's very interesting. This is because remember that the tensor algebra is the mother of all associative algebras. Every associative algebra is the quotient of a tensor algebra by an idea, right? So if you want, what happens here, and this is, I guess, why these path algebras were so extensively studied in representation theory, is that you kind of explore this, but now you add some more fancy combinatorics going beyond the Hawaiian earring. Even just for a Hawaiian earring, you can say absolutely every associative algebra is the quotient of the path algebra by Hawaiian earring. That's it. It's true, because the tensor algebra is right here, right? But the thing is, and I'm definitely not going to talk about it, is that when you study, say, finite dimensional algebras over some fixed field, okay, what you can do is the following. For any such finite dimensional algebra, you can construct so-called Gabriel's squeezer or directed graph. So you have an algebra, which is finite dimensional. There is a very smart recipe which produces a graph, okay? And there's an equally smart recipe which produces ideals in path algebra of this graph. And lo and behold, the quotient of this path algebra by this ideal is isomorphic with the algebra I started from. Yeah, so you can present finite dimensional algebras, maybe under some assumptions, as quotients of path algebras. And this is exactly what is used in representation theory and in classification of finite dimensional algebras. Okay, because you can somehow, the idea is that when you want to study representations of algebras, what you do, you present them as quotients of path algebras. And then in order to study modules, what you do, you put at every vertex of the graph a vector space, and to every edge, you assign a linear map. And then classifying, finding representation boils down to solving linear equations. So people who do representation theory love it. I mean, there's a whole Bible of Skowroński, Sims. I wouldn't dare to say algorithmic, but it's something which is very tangible, right? I mean, instead of some abstract modules of a ring, you say, okay. I first turn my algebra into a quotient of a path algebra, okay? Then it's very easy. Once you have such a representation of your quiver by vector spaces and morphism, you can very easily say, aha, so this is a module of your path algebra. And then basically you have to say that the idea of relation must be respected by these morphisms which you have in your quiver. And you solve linear equations. That's not what I'm going to talk about, so you'll not force me to write anything. This is like off the topic, but this is absolutely essential part of mathematics. I mean, yeah, you have this blue book, we have a Bible by, which is called Representation Theory by Skowroński, Assem, and one more guy, I forgot, 3 guys. Okay, seems. Okay, but let's go back to path algebras. Well, if you take the Hawaiian earring with n loops, but you can have uncountably many loops, so you are not bounded by the finite dimension. It's easier to draw n loops than uncountably many loops. That's why I didn't have time for drawing uncountably many loops. Then simply this path algebra is the tensor algebra. So you have a field, and then you have tensor powers of your vector space, which is an n-dimensional vector space. And you can also think about it as a non-commutative ring of polynomials in n variables, right? It's the same thing. And the identification is obvious. The only paths you can have are these words. EI1, EI2, and so on and so forth. These are the only paths you can have in your path algebra. And then you can use the same indices, which vary. Each of these indices, E1 to En, varies from 1 to n. Okay, and you map to this chi with such a path. You map it into the elementary tensor Fi1 tensor dot Fim, where Fj is the basis of your vector space.
The notation is really a safe notation.
Yes.
You wouldn't dare to write v to the 0 is k.
No. I was afraid of it. Yes, I chickened out. Yes, you're right. I could have done it. I could have done it. Yes, you encouraged me. So I will remove this.
After all our discussion on the importance of b, or the antiproduct being the one.
Okay, you got. All right. I'm a victim of my own teaching. All right. And now we are slowly approaching the centerpiece definition of my today's lecture, namely the Levitt path algebras. And of course, Levitt would never recognize this definition. He did not define it. Okay? But you'll see in a second why it's been baptized by his name. Okay, and here is somehow funny because here graph sister algebras, which were much earlier than Levitt path algebras. Unlike in quantum groups were much later than Hopf algebras. Okay. So here Levitt path algebras were basically invented or discovered in 2004, whereas Kuntz and Krieger did graph sister algebras in the 1980s. So this algebraic stuff came like 24 years later. But I want to do it not historically, but logically. I want to follow the natural path of constructing things in mathematics. Okay? So that you understand what's going on. All right. So let E be a graph, K be a field, and reg of E be the set of all regular vertices in E. I told you that is important. I told you. Now I'm keeping my word. I need to distinguish regular vertices from other vertices. And at most finitely many. Yeah. So the Levitt path algebra, denoted as LKE of a graph E, is the path algebra of the extended graph. This is important. It's not the path algebra of a graph. It's the path algebra of the extended graph, okay, divided by the ideal generated by the union of the following sets. And these are so-called Kuntz-Krieger relations of type 1 and type 2. So type 1 is simpler. You see, this is why this graph situation is asymmetric. Yeah, because the starred elements play a different role than the non-starred elements. Okay, the second relation is more difficult than the first one. That's why we care about sinks, but we don't care about sources. Okay. So what is the first relation? The first relation tells you the following, that if I take an edge E and an edge F, okay, then when I have an edge E, then of course I have a ghost edge E star. This is a path in the extended graph. So I can take chi E star. I can multiply it by chi F, okay? And in my algebra, it must be equal to the Kroneker's delta between these two edges times chi of the vertex, which is the end of path E. And if you ask why path E, not path F, well, of course, when E is different from F, it's 0 anyway, but if E is equal to F, then it doesn't matter if it's the end of E or F, they're the same, okay? So basically what I'm saying here is that edges are isometries with orthogonal ranges. When we go to sister algebras, that's what you'll see. The isometries with orthogonal ranges. So that's kind of easy, right? That's kind of easy. What is far more difficult to handle is the second, so maybe I should write this, this is Kuntz-Krieger. The second relation tells you the following. This is why you need a regular vertex, because then the sum is non-empty and finite. Okay, when my vertex is regular, then this sum, this set is non-empty and finite. Okay, so it's really meaningful. And now, mind you, I reverse the order Now, non-start edge goes first and start edge goes next. Okay. But now you see the first relation is really about edges. I'm telling you that if I have two different edges, then chi E star times chi F is 0. That's it. They miss each other. But if E is equal to F, then what I do if I have chi E star times chi F and I multiply them together, then I must get just the projection, which is the end of this edge. So I'm telling you that this is a partial isometry. Okay. So this is about edges, the first condition. The second condition is about vertices. Because I cannot tell you what is chi E times chi E star, because this depends on how many other edges are shooting off this vertex. So in particular, if this vertex is in infinite diameter, this is completely cancelled. There's no relation whatsoever. Okay, it must be a regular vertex. But if it is a regular vertex, I'm telling you that I take all edges emitted from this regular vertex. I take all these idempotents, which are chi E star. I sum them together, and guess what? I get chi assigned to the projection, which is the source of all these edges. Okay, so maybe I should draw a picture here. So I have E, and I have the ghost E star. So I'm saying that this way times this way is just this vertex. So in other words, I'm collapsing it, like particle and antiparticle, they collapse, evaporate, and only this hole remains. Okay, yeah. But only E star. If I have E and F star, forget it. That's just 0. Nothing happens. But if I have E star and E, then I collapse to this edge, but not the other way around. Okay, I'm telling you only E star times E. When I take E star, no, I know nothing yet.
So no relation, no nothing.
No, not yet. Okay, so that's the second relation tells me. So this is about edges, because I don't care what happens at this vertex. I don't care. I can have 1 billion of other edges being emitted from this vertex or ending at this vertex. I just do not care. The relation still holds because the relation about edges. Now the second is about vertices. So first, I demand my vertex to be regular. And when you are regular, well, you just emit finitely many edges, okay? Right? Say E1, say let's E, F, and G. Okay? And now I'm saying that E, and this is my V. I say that E, let me skip, like allow me to skip writing these chi's, right? I mean, of course, that's not really nice for legal purposes, but I think as for an explanation on the side, it's good enough. So E star plus FF star plus GG star is equal to V. And that's my relation. Okay. So here it's very important. I go by E, I go back by E star. I go by F, I go back by F star. I go by G, I go back by G star. And I add these 3 loops together, and then they add up to this vertex. But only all of them. If I forget the GG star, that's nothing. I don't know what it is. Okay. And if V is infinite diameter, there's no relation. And of course, if V is a single, there's also no relation because there are no edges. Okay. All right. Well, I have a certain proposition. You should have expected it. Yeah. Well, going back to our good old friend, complex numbers. We are going to put a star. So E is any graph, but now I want my field to be the field of complex numbers. And now I say that these formulas define an involution on the Levitt-Papp algebras, rendering it a star algebra. Well, that's an easy exercise. Immediately say it. Let's see it. So vertices are self-adjoint.
So associativity is automatic.
Associativity of what?
Leaving part out.
Levitt? Yes, of course, because at the moment you prove that path algebra is associative, a quotient of any algebra by D is an algebra. That's automatic. Yeah. Now, when you look at the star, and now I'm using sort of that these things are defined by generators and relations. I kind of brushed it under the carpet, but it's really very easy. If you go to the definition of a path algebra, you can also define it as an algebra given by generators and relations, with generators being paths of length 0 and length 1. Why? Because any other path can be composed, can be obtained by multiplication, by concatenation. Okay, so these are algebraic generators. And then you have very simple relations also given by concatenation. So all your vertices are orthogonal idempotents, and a vertex times an edge is equal to 0 if it's not the beginning. If you multiply from the other side, it's 0 if it's not the end, and it's this edge if it is the end, blah, blah, blah. I mean, the usual things. So you can very easily write down the path algebra as the universal algebra given by generators and relations. And I'm using the same generators, I'm throwing in more relations, okay? That's why in order to verify that a certain map is well defined, all I have to do is to verify that it satisfies the relations in this ideal, okay? So of course, you should also see that it all works nicely for the path algebra itself. I'm not proving this proposition, but it's really a trivial exercise, okay? It's really a trivial exercise. And I'm just telling you how to do it. What is the logic? Present Levitt path algebra as the universal algebra given generators and relations, and then you check that the relations are preserved by these formulas. That's it, and you are done. Now let me just do it for these relations so that you see how it works. It's completely trivial on that side, because if I apply this formula, so okay, so chi v star is chi v, chi e star is chi of e star, and chi e star star is chi e. So obviously it's an involution, okay? I mean, the square is identity. If I apply it twice, I land back where I was. And you know, by extension, it is you just assume it to be anti-multiplicative. That's by assumption, right? And you have to see that it really works. So yeah, I apply it here. So I have chi e star star chi e star minus chi v star, but it's the same thing. It's the same thing because, right? Because chi e star star is chi e, and chi e star is chi star, and chi v star is chi v. So that's just equal. So by starring every summand, I go back to where I was. So of course, this is preserved. It's a bit more tricky here with the first relation. You have to somehow do two cases. One case when E are different, E is different from F, then this Kronecker delta is just 0. And when I do chi E star chi F star, I obviously get chi F star chi E, but still E is different from F, so it's still in the ideal, okay? And when E is equal to F, I have chi E star chi E minus chi TE. Again, I apply the star. This is self-adjoint. This I flip around, but when I have chi E star is chi of E star, and chi E star star is chi E. So it's again in the ideal, right? So you very quickly verify that indeed this is well defined. It gives you an involution, rendering my complex Levitt path algebra into a star algebra. Okay, and you can guess precisely why I'm doing it, because then I'll apply the universal sister algebra construction. But okay, first let's talk some examples. Before we complete, let's do some examples. So first, when your set of vertices, edges is, one of the nightmares when lecturing about graphs, graph algebras, is this constant slip of a tongue confusing vertices and edges. You did it as well. I mean, it's almost impossible not to make such a mistake. When there are no edges, all right, then the Levitt path algebra is nothing but the path algebra, right? Because these relations are vacuous. I mean, all these relations involve edges. So there are no edges. These relations do not exist. These sets are empty. Okay. I label it by a regular. Of course, when I have no edges, no vertex is regular, right? Because all of them are things. So this set is empty and this set is empty. So the ideal is 0. So it's just a path algebra, the path algebra of E. Okay. And as we established, when I have the path algebra of E, where E is a graph with no edges, this is just a function algebra, just commuted. So that's first example. Well, how about another one? And finally, we're getting to something we like, full matrices. Okay. So I have the same graph as before. This is just a finite path from V1 to Vn. I have n-1 edges and I have n vertices. Then this Levitt path algebra of this graph is the algebra of matrices, and the isomorphism is the isomorphism of star algebras. In fact, of C-star algebra, because the completion does nothing. This is finite dimension. Okay. Okay, but I needed the extended graph. You see, here I can go back by ghosts. This is why I need an extended graph. So I can go back by ghosts. So not only I'm upper triangle, I'm also a lower triangle, where lower triangle part is given by antiparticles and upper triangle is given by particles. No, diagonal. On diagonal, you have vertices. Yeah, a path from V2 to V2, a vertex. Okay. Now, how about going to infinity? I remember when I was in high school, and I really not joking. When I was in high school, I had a dream. I had a dream that I was at infinity, and I saw the limits of all divergent sequences. This was a tremendously beautiful dream. And you actually physically at infinity. Oh, the sum of all inverses. That's here. The sum of all ones. It's here. All divergent sequences were there.
It's like here, Divina Commedia. There is in the last chapter there is the vision of God with Dante as. So
okay.
Maybe.
Yeah.
My memory is not strong enough to recall all the details, like in this case.
Yes. Anyway, this is a fun dream. So how about marching off to infinity to the right? Okay. So we have just a graph is a path, a simple path, but it goes to infinity. It has infinitely many edges. So the algebra is not unital. Okay. It has infinitely many vertices. So the algebra is not unital because it has infinitely many vertices. Okay. And now, guess what? The Levitt path algebra is the star algebra of all finite rank matrices. And of course, the algebra of all finite rank matrices is non-unital. Okay. You don't need compact operators. So here, the C-star algebra and the Levitt path algebras are different. Now, if I would complete it, I would get, of course, compact operators.
So if we know all finite graph matrices of vertices.
Well, the union.
Not by rank, you mean n times n by s?
Size, yes.
Or in the size.
Let me not write 0 by 0 matrices. Sorry. Sorry, I forgot to switch off my phone. Well, you multiply as you multiply matrices. This is a matrix algebra, and you have this union, okay, by saying that Mn C in Mn plus 1 C. Sorry, I have a question. You have to call later. Is embedded in the obvious way. I mean, here's your block n by n. Here's your matrix.
I embed.
Yeah, embed. Just like you do compact operators. Just you don't complete. What do you mean by? Yes. But it's just a union. The moment I tell you how I view n by n matrices as n plus 1 by n plus 1 matrices, I'm done. But you're right. This is actually disconstructing a limit. Yeah, sure. But it's so simple that you don't have to, use the magic word. Yeah. And so these are, if you want arbitrary size finite matrices, it's also a way to put it. Arbitrary size finite matrices. Okay. And of course, we multiply them because for two matrices which are arbitrary size but finite, you will find the biggest common denominator, and then you multiply. It's no problem. Okay. And as a star algebra, but it's obviously non-unital. I mean, there is a unit, but it's in the multipliers. Okay. But now, how about our one loop friend? It used to be a polynomial algebra for path algebras. But now, because I have a ghost, this becomes a unitary. And these are Laurent polynomials. Okay? Because you see, by one relation, by the first conspicuous relation, let's call it E. Yeah, remember, let X be a space, call it Y. This is okay. I know that E star. I know that E star E is equal to V, but it's just one vertex, so it's equal to 1 in my algebra. So this is by the first conspicuous relation. Yeah, number 1. Okay. I have only one vertex. The end is which is the end of my loop, but it's 1 in my algebra. But now look here. Oops, what did I write down? This vertex also emits only one edge. So the sum is a one element sum. It's a regular vertex. And this is a sum over one element. But now I write E star, but it's again equal to my vertex. So it's a unitary. For the second conspicuous relation, I have E star is equal to V is equal to 1. So this is precisely the unitary. Okay, and I have a Laurent polynomial. Nice commutative thing. And of course, the isomorphic S star algebra. Okay, but all of this is really trivial. I mean, you can very easily convince yourself that it's the case. These two cases are actually hard to prove. Ludwig, this you can put on an exam. This, unless you want to fail students, that's only if you want to fail something. I mean, it's not a big deal, but it's not something you will do offhand immediately and without thinking, right? Here, what I'm trying to say is that when I try to combine two pictures, all right? I have something like a circle algebra, because let's not fool ourselves. When I complete Laurent polynomials, I get continuous function in a circle, okay? Right, that's it. So here I have a circle algebra, here I have matrices. So how about combining the two? Well, we can do it. You can have a loop, which is not a simple loop of length 1, but it's a loop of length n. I have n edges conspiring to be a loop. And then I claim, but this is a non-trivial claim. It requires a proof which is quite ingenious. I mean, for hindsight, it's trivial, but for hindsight, almost everything is trivial. Fermat's theorem is trivial after 400 years, not before. So you can really verify that the Levitt path algebra as a star algebra is nothing but, say, Laurent polynomial with coefficients being matrices size n, or you can say that you have a matrix algebra with entries being not numbers but Laurent polynomials, or you can simply say that it's a tensor product algebra run by matrices with Laurent polynomials. That's all the same thing, obviously. But it is the Levitt path algebra for this graph, which is non-obvious. Okay. Nevertheless, it's true, and it's fun to prove it. I mean, don't take me wrong; it's not something hard research-wise. Yeah, I mean, if you put it into any master student, next day there will be a solution. But it's not something that I would dare to do offhand. Okay. We wanted an infinite graph. We have an infinite graph. I have countably infinitely many edges from vertex V to vertex W, from V to W. And it's something very fascinating, because this is the minimal unitization of the previous algebra of all finite rank matrices. Okay, I'm just throwing a unit. I have a non-unitary algebra, and I told you how to unitize a non-unitary algebra. I told you. And here I'm telling you that if I take the Levitt path algebra of this graph, and of course it must be unital because I have just two vertices. Okay, so the unit is V plus W. V plus W equals 1. This is a unit of algebra.
And you said the infinite matrices were the infinite edges, infinite vertices with one edge.
What
Without the plus, the graph was infinite vertices and one edge.
why one edge?
Well, I was trying to.
Why one edge? You have infinitely many edges.
But this graph from
Yeah, this graph. That's the graph.
okay, between two consecutive vertices.
You have one edge. Yeah.
One edge.
Oh yeah. But you didn't say the magic word, consecutive vertices. Yes.
Yeah. Okay.
Yes.
It's incredible. So the
Yes.
organization is completely different.
Yes. I know. So I want to propose you an open research problem. I'm serious. Okay. So here's the result. Again, it's research-wise is trivial. I mean, you give it to any mathematician after lunch, you'll have a solution. But I would never dare to put it as an exam question. Okay, you can prove it, but you have to sweat over it a little bit. But it's still true that the Levitt-Path algebra, as a star algebra, is nothing but the minimal unitization of the algebra of finite rank matrices.
So what's the meaning of this?
Countably infinitely many edges. I explained it. Countably infinitely many edges. What's difficult? I cannot draw infinitely many arrows. So I put this little 8 here. Yeah. But you should think that I have edge E0, E1, E2, blah, 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 up to infinity. Both, all of them, beginning and ending at V and W respectively. Okay. So that's something very beautiful and not something that you'd expect.
So, well, then further is a map, like you can map the set of the path, right? From this.
Of course. I mean, of course. I mean, what else do we expect? What happens here is that this algebra is infinite. I mean, algebras are infinite because we have infinitely many paths. If you have finitely many paths, when path algebra is finite dimensional, you divide it by relations, you know. Although you have, it's a bit tricky because remember, the moment I draw a graph, when I do Levitt path algebra, I always go to the path algebra of extended graphs. I always have loops because I always have ghost edges. So there is no extended graph without loops unless it is just vertices. Okay. So there are loops. However, these loops are collapsed by the relations, and this is still finite dimensional. In fact, to be honest, to prove that this is an algebra of matrices, it is trivial provided we have a basis theorem. And a basis theorem for Levitt path algebra is a beautiful and tough theorem. Yeah, the moment you have a basis theorem, but you know what your basis is, because you see, I'm quoting first I'm extending and then I'm dividing. So that's a complicated procedure. It's totally non-obvious. What is obvious what spans your vector space. Okay, but it's totally non-obvious what are linearly independent elements. That's totally non-obvious. And the answer is quite subtle. But we have an answer. There is a theorem. And once you know this theorem, you can easily prove it. Aha, so the Levitt path algebra is really the matrix algebra. When you have a basis theorem, that's trivial. That's not trivial even with the basis theorem. And the same is true here. But sorry, but I didn't finish my thought. So obviously, roughly speaking, what happens is that, like over there, you have infinitely many paths. You have infinitely many edges. Well, an edge is a path. So you have infinitely many paths here, infinitely many paths there. But it's not so obvious how you make a nice map, which is an algebra isomorphism. You can do it, of course. But it's something which requires a little bit of thinking. Not much, but you know. As a research problem is trivial. As an exam question is hard. Okay. So before I give you this research problem, I want to explain to you why poor Guy Levitt is involved here. This was a guy who published an interesting paper in the 60s, I think, 62, so it's before I was born. And he was interested in the following problem. Given two different natural numbers, say m and n. Find me a universal ring with a property where the free module Rn is isomorphic as a module to a free module Rm. And for each such a pair of different natural numbers, he constructed a universal ring with this property. And these are Leavitt algebras. Okay. So in particular, when I look at my Hawaiian E-ring, this is a very beautiful graph, Hawaiian E-ring. And I look at the Leavitt-Pav algebra of this Hawaiian E-ring, so it's no longer the tensor algebra because I divide by relations, okay? I say that this is actually isomorphic to Leavitt-Pav algebra for indices 1 and n, where n is the number of loops. And it gives me a certain, I can explain in what sense it's universal, but it gives me an algebra with this beautiful property that when I take the nth power of my algebra, so it's a free module, right? I take n copies of my ring. This is a free module, right? But it's isomorphic as a module to just algebra itself.
So as module over LK.
Exactly,
Okay.
exactly. Okay, so there are rings with the property that Rn is isomorphic to Rm as modules with m different from n. And this is what Leavitt was working with.
Incredible.
And this is the solution. And these algebras are universal in some mild sense, in the sense that every ring with this property must somehow uniquely factor through his ring, stuff like this. I don't want
So
to.
is this what you were referring when saying, yeah, there are not free modules?
Yes, exactly.
There's no
dimension. There's no dimension. So be very careful when you have free modules. You cannot say I have a free module of dimension n. You are talking nonsense.
Yeah.
Because I have a basis with m elements, have a basis with n elements, and m and n are different.
The hypothesis was like the ring must be, for example, local.
The
In this
ring,
case, we can.
there's a very simple criteria. The ring must not have any finite dimensional representations.
Okay.
Okay, that's it. Because the moment you have a finite dimensional representation, you go into matrices over a field, and we have a matrix over a field. A matrix over a field is invertible if and only if it's square. You don't have rectangular, properly rectangular matrices over a field that are invertible. But here you do. Look what happens. Look at these two relations. I have my first Kunstkrieger relation and my second Kunstkrieger relation. It means that when I write a matrix like this, I have chi E1 dot 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 chi En. I multiply it like this by chi E1 star chi En star, and this is a unit matrix, right? By this rule. But I multiply the other way around. So this is bra and cat, now cat and bra. I multiply it like this. Like a scalar product, you know? And this is 1 by this relation. So I showed you a rectangular matrix, properly rectangular matrix, which is invertible. So this establishes this isomorphism. Isn't it cool? I think it's really beautiful.
So the bottom line on the second is relation.
Yeah. So this implies this, and this implies that.
But one is the same as the identity matrix, or as a different element.
One is always one in this ring. I mean, this is one. I mean, this is chi of this vertex. This is one.
Okay.
So that's amazing. And obviously, this algebra has no finite dimensional representation, because if it did, that's correct. No finite dimensional representation, because then I would substitute k by some vector space of dimension k. And I would have dimension nk and dimension mk. Sorry, but mk must be equal to nk. And if k is non-zero, m is equal to n, contradiction. Okay. So these are guys without finite dimensional representations. All right. There are whole books written about rings without basis property. There are whole books studying such rings. But Leavitt was looking for such a universal example in 1962, and these are called Leavitt algebras, not Pav algebras, Leavitt algebras. But Leavitt algebras are special cases of Leavitt-Pav algebras. But Leavitt-Pav algebras are 2004. So Leavitt is 1962. and Levitt path algebra is 2004. Okay, so quite a big difference. Well, so I have like 5 minutes. So I have to tell you this conjecture. It's really a lot of fun. So you see, and it's an open problem. It's an open research problem. Okay, I saw only one paper about unitizations of graph sister algebras, and it doesn't concern this issue. And I consulted with experts. Okay, so you see what happens when I have a path which marches off to infinity. I sort of make it like a telescope. I shrink it to just 2 vertices, but they've countably infinitely many paths. I conjecture that if you have a tree with some branches marching off to infinity, I could just shrink them telescopically in such a way that between appropriate 2 vertices, I would have countably infinitely many edges, and this would be the minimal unitization. But it's a conjecture. If you prove it, it's a publishable paper. Okay. So imagine that instead of 1 branch tree, I have a complicated tree, and some of the branches of my tree go to infinity. Some, yeah. And at least one. if not one, it's unital. You have nothing to do, right? If any branch goes to infinity, I just I just shrink it to like I did before. I shrink it to a thick edge, if you want. I shrink it to a pair of vertices with countably infinitely many edges. And you can, of course, ask, well, how about if I have a branch, but between this vertex and this vertex, I have 5 different edges. And how about jumping edges? So I have an edge here, edge there, but I also have an edge there. So you have lots of things you can add here, right? But you should talk a tree. I mean, if it's not the tree, forget it. I think this would be something strange. Yeah, I mean, without the tree, I don't dare here to make any conjecture.
So the conjecture is for trees.
Yes.
Is this already improved for maybe case? Like
No. I mean, the only case is I told you here. Just 1 branch. Anything else is open.
So even in the case of the perfect fractal is not just
In case of what?
like the perfect fractal tree.
Yeah, of course not. No, nothing. Nobody cared about it. Because you see, I can tell you why nobody looked it up. We know it because we know Podlash. We know it because this is, in fact, when you go to sister algebra, this is the minimal unitization of compact operators, which every child knows is the sister algebra of a Podlash sphere. So because we are doing quantum geometry, we saw it. If you don't do quantum geometry, you would never bother. I mean, why bother with unitization? Because it's not obvious. You don't find it in books. I have a whole book where you have unitization, where you have this branch, but nothing about unitization of this branch. But I had to do it because this is my example of a quantum sphere. So that's why it's not solved. Not because it's difficult, but because nobody looked at it. Okay, now take home. I mean, yeah, Ludwig, you stole some minutes. So, but this is the last slide. This is the last slide. Okay. This is really a take-home message. So the whole lecture today was tuned so that I can deliver this theorem definition. Okay. So let E be any graph and let LCE be its Levitt path star algebra. Then first, there exists the universal enveloping C star algebra, C star E of this LCE, and the canonical star homomorphism mapping star algebra into its C star envelope is injected. We call the C star E the graph C star algebra of E. And well, so first you have to construct a bounded representation of Hilbert space. It's not easy, but you can do it. Then you prove that the intersection of all kernels of bounded representation is 0. That's a lot of work, but it's true. So here this tilde construction means nothing. I mean, these kernels really intersect to 0. So then later on, this canonical map gives you an injection, okay? And then there is the only thing which is easy here is that there is a common bound for all bounded representations, because here generators are given by projections and partial isometries. Okay, so if you take any bounded star representation, when I have a projection, I know that the norm of P squared is equal to the norm of P star P but is equal to the norm of p squared is equal to the norm of p. I mean, the only real number satisfying p squared is equal to, a squared is equal to a if a is 0 or 1. So the norm can be 0 or 1, so it's bounded by 1. And much the same way here, if I write down the norm of s star s, I skip the row, then it will be of course the norm of s squared, but it's of course the norm of p. So then the norm of s is the square root of 1 and 0. Again, it's 1 and 0, nothing else. So it's bounded. So that part is trivial. Okay. The moment you establish that there is a bounded representation, which is a nice construction, the moment you do a lot of hard work proving that the intersection is 0, that's a lot of hard work, a lot of graph theory. Okay. I mean, some graph theory. Then that you can complete this tilde is trivial because the bound exists. Okay. And this is where we will pick up next time. For the time being, let me stop recording and we adjourn till Thursday. Thank you so much. Stop sharing. Stop recording.